Welcome back, everyone. This is Professor Herring. In this video, we're going to continue looking at Lewis structures and the variations within them. Specifically, we're going to talk about a phenomenon that we call resonance. And we're going to understand how resonance structures work and the effect of resonance on properties such as bond order, bond length, and bond strength. So in the last video, one of the last things we looked at was drawing the Lewis structure for the nitrate ion. And we calculated the formal charge on the nitrogen as well as the oxygens. It turns out, though, that we just arbitrarily decided which oxygen formed the double bond with the nitrogen. And in this Lewis structure, it implies that there is a short bond and two long bonds. But scientists have done experiments and have found that all three nitrogen-oxygen bonds are actually the same length. And what this means then is that the structure as we've drawn it is not accurate. It does not accurately depict what we observe in real life. And so a molecule, we say, has resonance when there's more than one Lewis structure that can be drawn for a fixed nuclear arrangement. So what this might look like for nitrate is the following. If we label these as oxygen 1, 2, and 3, we could draw the double bond in different locations without actually changing the physical location of the elements. And that's what we mean by resonance. Because of these structures, what we see is that the bond properties, the bond order, the bond length, and the strength are averaged over the resonance structures. So in the structure in the middle, it looks like there is a bond order of 2 and 1 and 1. And where that bond order of 2 is, looks like is shifting. But in reality, the real structure is actually a weighted average or a blend of all of the resonance structures. And so it turns out that it is not any one of these structures, but it is the average of all three structures at once. And we can use dotted lines to represent the electrons that are delocalized between the resonance structures. So if any one of these resonance structures was true, what it indicates is that there are 2 electrons between these 2 bonds, or those elements, and 4 electrons here. But in reality, the truth is that there's 2 electrons in between each, and then 2 electrons are shared across the whole molecule. And this is just amazing to think about, because the electrons, they're not jumping around from one end to the next, but they are literally spread throughout the whole molecule. Think of it like a large blanket encompassing the molecule at once. And this has very important implications, because this is going to strengthen the bonds. What was a single bond is now somewhere in between a single and a double bond. So let's take a look at some of the details of this. What we're saying is that the true bond order is somewhere in between 1 and 2. Well, if you take an average between the different structures, what we can see is that the bond order is actually 1 1/3. Now, how do we get that? Let's zoom in and focus on, let's just say, this particular bond. And the bond order, in this case, is 2, 1, and 1. Well, what's the average bond order? The average is the sum of the parts over the number of parts. Our sum is a total of 4 bonds. But again, we're counting up these bonds in between nitrogen, and we'll just call this oxygen number 1. And there's 3 different forms, if you will. That gives us then 4/3, or 1.33. And that's our observed bond order. If you look at the bond strength, the longer or the lower the bond order, the weaker it is. So that means then that the nitrate bonds, the bonds within the nitrate, are somewhere in between a single and a double bond in terms of their strength, and that their length is inversely proportional to that. We can also, if we wanted to go through and calculate the formal charge, we said before that it was a positive 1 on nitrogen and negative 2/3 or a negative 1 on one of the oxygens. Well, it turns out that on the oxygen, it's not negative 1 or 0, but it's actually in between. If you were to take the average bond or the formal charge of this oxygen, here it's 0, here it's -1, here it's -1. So the formal charge average is -2 over 3 forms, negative 2/3. And we see that because resonance is increasing the number of electrons shared from 1 to 1 1/3 between them, that's going to stabilize the molecule. And that has important implications for how nitrate is going to react with other compounds. So let's take a look at some general characteristics of resonance. Molecules that have resonance, when they can be represented by several correct Lewis structures, differ only in the positions of the electrons. When we looked at the nitrate, the oxygen atoms, the nitrogen atom, were not changing locations. It was the electrons themselves that appeared to be changing locations. The arrangements of atoms and the total number of atoms and electrons must be the same. So in other words, in nitrate, you count up its number of electrons and you get a certain number. If you add an electron to that, that's no longer nitrate. That's not a resonance form of it. It's a different ion completely. And then finally, not all resonance structures are equally good. They don't always contribute the same. In nitrate, they did. In nitrate, all of the formal charges were the same. However, we could look at a structure here where in one case we have 0 formal charges, in the other case we have non-zero formal charges. And these non-zero formal charges don't contribute as much as the ones with 0 formal charge. You don't need to know the percentages and the exact numbers, but you should be able to predict that non-zero formal charge is better. And so the real structure of this molecule looks something like this, some intermediate in between the two different forms, with an emphasis on the form on the left. There are some patterns to look for when trying to determine whether or not resonance can exist. One of these patterns is looking for a lone pair that's adjacent to a double or triple bond. So in other words, if we have a molecule with elements X, Y, and Z, element X has a lone pair on it, and then it's adjacent to a double bond or a triple bond, then we can draw a resonance structure that would look like this. Okay, so what you have is you've got a lone pair on an element bound with a single bond. And it's attached to an element with a double bond. And in practice, this might look like the following. Oxygen with with some lone pairs. It's attached to a carbon that has a double bond. Those electrons could be shown to be moving, and we could draw a second resonance form. Something to keep in mind is that the electrons themselves are not actually moving from one form to the next. We're not shifting or transforming from one to the next, but really we want an average of the forms. So let's try a practice here. Of the following molecules, which are resonance structures? Well, the answer is 1 and 3. We've got a couple reasons for this. One is that in structure 2, we cannot exceed an octet. We can't violate the octet rules if they must be followed. We'll talk about violations of the octet rule later, but carbon cannot have an exceeded octet and still participate in resonance. 4 is showing that the hydrogen atoms have been moved from the nitrogen to the carbon, and therefore that's not the same structure. So only 1 and 3 represent resonance forms. We have a lone pair of electrons with a single bond and then a double bond next to it. We could draw those lone pairs moving here and then this moving there, and that gets us this structure here on the bottom. All right, I'd like for you to try out this problem on your own. Pause the video now and try this on your own to see if you can solve it. Welcome back. So in this question, we're asking you to rank them in terms of increasing carbon-oxygen bond length. Okay, so what do we need to do first? Let's start by drawing out the various Lewis structures. This is for the second structure, carbonate ion. The carbonate ion is going to have 24 valence electrons. When we draw out its structure, put carbon in the middle, oxygen's on the exterior with single bonds. Start by adding in the lone pairs of electrons. We see that we don't have enough, and therefore we draw a double bond between the carbon and the oxygen. Now, when you see this, in your mind, you should think that you could draw that, you could draw the double bond between any one of those oxygen atoms. And you could go through and calculate the formal charges. We're going to move on and look at the bond orders. So, as we saw before, we could have drawn carbonate in any one of these 3 structures. And therefore we know that its true form is some intermediate version of all of those. It has a bond order of 1 1/3. Again, you can calculate that by summing up the bonds between any 2 elements, which is 4, and divide by the number of resonance forms, which is 3. That gets us 1 1/3. When you draw the Lewis structures of carbon monoxide, you see that it has a bond order of 3, and carbon dioxide has a bond order of 2. And so we know that bond order and bond length are inversely related. And so the one with the shortest bond length, the smallest bond order has the longest bond length, and the largest bond order has the smallest bond length. So then we can rank them, and we see then if we want to go in terms of increasing carbon-oxygen bond length, that carbon monoxide is the shortest, carbonate ion is longest, with carbon dioxide in between. That's it for this video. If you have questions, please ask on Piazza, in office hours, or in recitation. Thanks for watching and have a great day.